50,000 years ago, the Arizona desert did not exist as we know it today. The landscape was different, covered by denser vegetation, inhabited by woolly mammoths and giant ground sloths that wandered beneath a sky that, at that time, still had no name. On that specific night, if any creature had looked upward, it would have seen only the common vastness of the stars, the same panorama of millions of luminous points that had repeated itself for ages. But something was approaching. A fragment of iron and nickel, approximately 50 meters in diameter and weighing 300,000 tons, was crossing the inner solar system at a speed of roughly 46,000 kilometers per hour. This object did not know it was about to create one of the best preserved impact structures on planet Earth. Meteor Crater, also known as Barringer Crater, in honor of mining engineer Daniel Barringer, who first proposed its extraterrestrial origin in the early 20th century, represents today a natural laboratory of extraordinary proportions. With a diameter of 1,200 meters and a depth of 170 meters, this circular depression in the Colorado Plateau holds within its stratified walls the geological memory of an event that lasted only a few seconds, but whose energy was equivalent to approximately 10 megatons of TNT. To put this in perspective, that corresponds to about 700 times the power of the atomic bomb dropped on Hiroshima. And it all happened in an instant so brief that if you had blinked, you would have missed it completely. Today, when researchers and visitors arrive at the rim of this crater in northern Arizona, about 60 kilometers from the city of Flagstaff, they encounter a peculiar silence. The desert wind blows constantly, carrying fine sand particles that, under mineralogical analysis, still reveal traces of material transformed by the impact. Shocked quartz grains, with their characteristic planar deformation features, tell a story that no human being witnessed, but that science can reconstruct with impressive precision. It is as if the rocks had kept a record, a physical memory of the moment when something from deep space touched this specific point on Earth's surface. The region around Meteor Crater possesses one of the lowest rates of light pollution in the continental United States, making it a privileged location for astronomical observation. On moonless nights, far from the lights of Phoenix and Tucson, the sky reveals the band of the Milky Way with a clarity that our ancestors knew well, but that most modern urban inhabitants have never experienced. There is a gentle irony that precisely in this place, where a celestial object caused so much transformation millennia ago, the night sky remains so accessible, so present, almost like a permanent invitation to look upward and remember that Earth has never been alone in its journey through the cosmos. And it is exactly here, at this point in the Arizona desert, where outer space left its most visible mark on the North American continent, that we begin our journey tonight. A journey that requires no haste, no urgent destination, only the willingness to let thoughts quiet down while we explore together what it means to live on a planet that has already been visited, touched, transformed by wandering fragments of the solar system. As you settle in and allow your body to relax, imagine the dark sky over Arizona, the stars emerging one by one in the twilight, and the silent crater guarding its secret of 50 millennia. This is a story about collisions, but not the kind that causes anxiety or fear. It is a story about the inevitable encounter between worlds, about the gravitational dance that moves fragments of rock and metal across distances our minds can barely conceive. And it is also a story about Earth, this planet we inhabit, which over its 4.5 billion years of existence has received countless cosmic visitors, most too small to leave a mark, some large enough to reshape entire continents. Meteor Crater represents an intermediate point on this scale, an impact significant enough to create a permanent structure, but not catastrophic enough to alter the global climate or drive species to mass extinction. The science that studies these events is called impact geology, and its practitioners spend entire careers deciphering the signatures left by ancient collisions. In the case of Meteor Crater, decades of research have revealed fascinating details about the original projectile, about the sequence of events that unfolded in fractions of a second during impact, and about the mineralogical transformations that occurred under extreme pressures and temperatures. Each rock fragment collected in the region tells part of this story, and together they form a geological archive of remarkable precision. It is as if Earth had kept a diary of that distant day, written in deformed crystals and inverted stratigraphic layers. For astronomers working nearby at observatories like Lowell Observatory in Flagstaff or the Naval Observatory in the mountains to the south, the presence of Meteor Crater serves as a constant reminder of the physical connection between Earth and the rest of the solar system. We are not isolated in a protected bubble. We share our orbital space with millions of asteroids and comets, most on trajectories that will never cross ours, but some on orbits that will eventually bring them dangerously close. Studying impact craters is not merely an exercise in historical curiosity. It is also a way of preparing for the future, of understanding the risks and, perhaps, developing means to mitigate them. But tonight is not about worries or apocalyptic scenarios. Tonight is about contemplation, about allowing the mind to wander through time and space while the body rests. The impact that created Meteor Crater happened in an era so remote that no human memory could reach it. The first Homo sapiens would only arrive in the Americas tens of thousands of years later, finding the crater already eroded, already integrated into the landscape as if it had always been there. And in a way, for the human time scale, it always had been. So as the night advances and sleep approaches gently, let us explore together the details of this story. Let us understand what happens when a piece of space metal meets the surface of a rocky planet at hypersonic velocities. Let us meet the scientists who dedicated their lives to deciphering these events. And let us, above all, find in this narrative a particular kind of peace, the peace that comes from recognizing our place in the cosmos, small inhabitants of a blue planet that has already been touched by the universe and that continues its silent journey around an ordinary star, in a peripheral arm of a galaxy among billions of others. If you are finding a sense of calm in these words, there are small ways to help this channel continue creating nights like this one. A like takes only a moment and helps others discover these quiet journeys through the cosmos. If something in this story resonated with you, leaving a comment shares that connection, and your thoughts are always welcome here. And if you know someone who might benefit from a peaceful hour of science and stillness before sleep, sharing this with them could be a gentle gift. There is no pressure, no urgency, simply options if you feel inclined. Either way, you are welcome here, under this same sky that has watched over Earth for billions of years. To understand what happened 50,000 years ago in what is now northern Arizona, we first need to understand where the impactor came from. The object that created Meteor Crater was not a random piece of debris floating aimlessly through space. It had a history, an origin, a journey that began long before it ever approached Earth. And that story takes us back to the formation of the solar system itself, approximately 4.5 billion years ago. In the earliest phase of our solar system's existence, there was no Earth, no Mars, no Jupiter. There was only a vast cloud of gas and dust, rotating slowly around a young star that had not yet fully ignited. Within this cloud, particles began to collide and stick together, forming larger and larger clumps. This process, known as accretion, eventually produced the planets we know today. But not all material was incorporated into these major bodies. Vast amounts of rock and metal remained scattered throughout the solar system, particularly in a region between Mars and Jupiter that we now call the asteroid belt. The asteroid belt is not the dense, chaotic field of tumbling rocks that science fiction movies often portray. In reality, the distances between asteroids are enormous, and a spacecraft passing through would likely see nothing at all with the naked eye. But over astronomical timescales, the gravitational influences of Jupiter and the inner planets can disturb these orbits, sending some asteroids on new trajectories that cross the paths of Earth and other worlds. The object that struck Arizona was one such wanderer, a fragment of iron and nickel that had spent billions of years in relatively stable orbit before something nudged it onto a collision course with our planet. What made this particular impactor unusual was its composition. Most asteroids in the belt are rocky or carbonaceous, meaning they contain significant amounts of carbon compounds and hydrated minerals. But a smaller percentage are metallic, composed primarily of iron and nickel, the same elements that make up Earth's core. These metallic asteroids are thought to be fragments of larger bodies that were once differentiated, meaning they had grown large enough for heavier elements to sink toward their centers, forming metallic cores surrounded by rocky mantles. At some point, these parent bodies were shattered by catastrophic collisions, exposing their metallic interiors to space. The impactor that created Meteor Crater belonged to this class of objects. Analysis of the meteorite fragments found around the crater, collectively known as the Canyon Diablo meteorites, reveals a composition of approximately 92% iron and 7% nickel, with trace amounts of cobalt, phosphorus, and other elements. This composition is consistent with a fragment of an asteroid's core, a piece of metal that once lay at the heart of a much larger body somewhere in the asteroid belt. When scientists handle these fragments today, they are touching material that predates Earth itself, metal that condensed from the solar nebula before our planet had even begun to form. The journey from the asteroid belt to Earth is not a quick one. Even at the relatively high orbital velocities typical of near-Earth asteroids, the distance involved is measured in hundreds of millions of kilometers. The impactor may have spent thousands or even millions of years on its Earth-crossing orbit before the fateful encounter occurred. During this time, it would have completed countless orbits around the Sun, occasionally passing close to Earth or other planets, each encounter subtly altering its trajectory. The final approach was not a dramatic plunge from the outer solar system, but rather the culmination of a long, slow, gravitational dance. As the object approached Earth 50,000 years ago, it was traveling at approximately 46,000 kilometers per hour relative to our planet's surface. This velocity is typical for asteroidal impacts and represents the combined effect of Earth's orbital motion and the asteroid's own trajectory. At such speeds, the impactor crossed the final 1,000 kilometers in less than a minute and a half. There was no warning, no visible fireball streaking across the sky for extended periods. One moment, the Arizona sky was clear and calm. The next, a brilliant flash of light, brighter than the sun, marked the moment of contact. The asteroid entered Earth's atmosphere at a shallow angle of roughly 45 degrees, coming from the north-northeast. Atmospheric passage at such velocities generates tremendous heat through compression of the air ahead of the object. But for a dense metallic body of this size, the atmosphere provides only minimal resistance. Unlike smaller meteoroids that burn up completely during entry, the Canyon Diablo impactor reached the surface largely intact, having lost only a small fraction of its mass to ablation. The energy it carried was not dissipated in the atmosphere, but delivered directly to the ground. What happened next occurred in approximately 10 seconds, though the most violent phase lasted only a fraction of that time. The impactor struck the surface and was almost instantaneously decelerated from hypersonic velocity to zero. This deceleration released energy equivalent to 10 megatons of TNT, roughly 700 times the yield of the Hiroshima bomb. The energy was converted into heat, pressure waves, and kinetic motion of the target rock, initiating a sequence of events that would excavate a crater more than a kilometer across. Consider for a moment what it means to stop a 300,000-ton object traveling at 46,000 kilometers per hour in a fraction of a second. The forces involved are beyond any everyday experience. The impactor did not simply punch a hole in the ground like a bullet entering wood. It generated pressures exceeding 1 million atmospheres at the point of contact, pressures so extreme that rock behaves not as a solid, but as a fluid. The impactor itself was completely destroyed, vaporized and melted by the energy of its own deceleration. What remains today, scattered across the surrounding desert, are fragments that broke off during atmospheric entry, not pieces that survived the impact itself. And so as you lie there in the quiet of this moment, consider the strange journey of that metallic fragment. Billions of years drifting in the cold void between Mars and Jupiter, a gravitational nudge that sent it spiraling inward. Thousands of orbits around the sun, each one bringing it slightly closer to its destiny. And then, in less time than it takes to draw a breath, an encounter with Earth that ended its cosmic wandering and created a feature that would endure for tens of thousands of years. The impactor no longer exists in any recognizable form, but its legacy remains, written in the rocks of Arizona, waiting for anyone who wishes to read it. If you feel your thoughts beginning to drift, that is perfectly fine. The story will continue at its own pace, and you can follow along or let the words wash over you like gentle waves. There is no test at the end, no requirement to remember every detail. Only the invitation to rest, to breathe slowly, and to contemplate the quiet connections between our small lives and the vast movements of the cosmos. To describe what happened in the seconds following contact, scientists use the language of physics and geology, but even the most precise technical terms struggle to convey the sheer violence of an impact event. We are accustomed to thinking of the ground beneath our feet as solid and permanent, an unchanging foundation on which we build our lives. An impact of this magnitude reveals that solidity as an illusion, a temporary condition that can be shattered in an instant by sufficient energy. When the Canyon Diablo impactor struck the surface, it encountered a sequence of sedimentary rock layers that had been deposited over hundreds of millions of years. The uppermost layer was Moenkopi sandstone, a reddish formation laid down during the Triassic period when this region was a coastal plain. Beneath that lay the Kaibab limestone, a much older formation from the Permian period when Arizona was covered by a shallow sea. And below that were even older rocks, the Coconino sandstone and the Supai formation, each representing a different chapter in Earth's geological history. The impactor did not discriminate among these layers. It excavated them all, mixing formations that had been separated by tens of millions of years of geological time. The impact process can be divided into three main phases: contact and compression, excavation, and modification. The first phase, contact and compression, lasted only a tiny fraction of a second. During this phase, the impactor penetrated the surface while a shock wave propagated both into the target rock and back into the impactor itself. The shock wave traveling into the ground compressed the rock to pressures exceeding 1 million atmospheres, while the wave traveling back through the impactor destroyed it almost instantaneously. At the interface between impactor and target, temperatures reached tens of thousands of degrees, sufficient to vaporize rock and metal alike. The excavation phase began as the shock wave expanded outward into the target rock. Behind the shock front, the compressed rock began to flow outward and upward, excavating a bowl-shaped cavity that grew rapidly in size. This is not like digging a hole with a shovel, where material is removed piece by piece. The entire mass of rock within the growing cavity was set in motion simultaneously, flowing like a fluid under the extreme pressures involved. Some material was ejected at high velocity, arcing through the air to land as an ejector blanket surrounding the crater. Other material flowed along the crater walls, contributing to the raised rim that still surrounds the depression today. One of the most distinctive signatures of an impact event is the presence of shocked minerals in the target rock. When rock is subjected to pressures above certain thresholds, its mineral structure is permanently altered in characteristic ways. Quartz, one of the most common minerals in the Colorado Plateau sandstones, develops what are called planar deformation features, microscopic lamellae that form along specific crystallographic planes. These features are found only in rocks that have experienced shock pressures above approximately 8 gigapascals, pressures that do not occur in any ordinary geological process. At even higher pressures, quartz transforms into denser polymorphs called coesite and stishovite, minerals that were first discovered in the laboratory but have since been found at numerous impact sites worldwide. The discovery of these shocked minerals at Meteor Crater in the 1960s provided definitive evidence for the impact origin of the structure. Before that, there had been considerable debate about whether the crater was volcanic in origin, a possibility that seemed plausible given the volcanic history of the nearby San Francisco peaks. But volcanic processes cannot produce the pressures necessary to form coesite or stishovite, and the presence of these minerals proved beyond doubt that the crater was created by a hypervelocity impact. This discovery had implications far beyond Arizona, providing a template for identifying impact structures elsewhere on Earth and on other planets. The excavation phase lasted only a few seconds, but in that time, approximately 175 million metric tons of rock were displaced. Some of this material was vaporized or melted, but most was simply moved, either ejected from the crater or pushed aside to form the raised rim. The final cavity was roughly bowl-shaped, though somewhat asymmetrical due to the oblique angle of impact. The transient crater as geologists called the initial excavation, was deeper than what we see today, but subsequent modification would alter its shape. The modification phase began immediately after excavation was complete. The steep walls of the transient crater were unstable and began to collapse inward, sliding down toward the crater floor and partially filling the original cavity. This is why Meteor Crater today is shallower than it was immediately after the impact. The floor has been raised by fallback debris, while the rim has been lowered by erosion and slumping. Studies of the subsurface structure using seismic techniques reveal that the original crater extended significantly deeper than the present surface suggests, with a layer of breccia, fractured and mixed rock, filling the lower portion. Around the crater, the ejecta blanket spread outward in all directions, thinning with distance from the rim. Close to the crater, this blanket consists of large blocks of upturned sedimentary rock, some weighing hundreds of tons, that were flipped and rotated during excavation. Farther out, the ejecta becomes finer, consisting of smaller fragments and shocked particles, and scattered throughout this debris are fragments of the impactor itself, the Canyon Diablo meteorites that have been collected by scientists and enthusiasts for over a century. These metallic fragments, some as small as grains of sand, others weighing several hundred kilograms, represent the only surviving pieces of the original object. The sound of the impact would have been catastrophic, a thunderclap beyond anything produced by natural weather phenomena. Animals within tens of kilometers would have been deafened or killed by the blast wave. Vegetation would have been flattened in a radial pattern extending far from the crater rim. A cloud of vaporized rock and dust would have risen into the atmosphere, spreading across the region before gradually settling. And then, slowly, silence would have returned to the Colorado Plateau, broken only by the wind and the settling of debris. Over the following days and weeks, the immediate aftermath of the impact would have given way to a new equilibrium. Rain would have begun to erode the fresh rim. Vegetation would have started to reclaim the surrounding landscape. Animals would have returned to investigate the strange new feature in their territory, and the crater would have begun its long transformation from a fresh wound in the earth to the weathered, stabilized structure we see today. 50,000 years of wind, water, and geological processes have softened the crater's edges and filled its floor with sediment, but the fundamental shape remains, a testimony to the power of an event that lasted less time than a heartbeat. As you rest there, perhaps with your eyes closed, imagine the stillness that followed the impact. Imagine the dust settling, the stars emerging in the night sky, the first curious creatures approaching the rim to peer into the strange new hollow in the ground. The violence was over almost before it began. What remained was simply a crater, a feature of the landscape, slowly being claimed by the quiet processes of geology that would shape it for millennia to come. For most of human history, Meteor Crater was simply there, an unexplained feature of the Arizona landscape. The native peoples of the region, including the Navajo and Hopi, would have encountered the crater during their travels across the Colorado Plateau, though we have limited records of how they interpreted its origin. It was not until European American settlers and explorers arrived in the late 19th century that the crater began to attract scientific attention, and even then, the true explanation for its formation remained elusive for decades. The first documented scientific visit to the crater occurred in 1891 when a mineralogist named Albert Foote examined some unusual metallic fragments that had been collected near the site. Foote recognized these fragments as meteorites and noted the presence of tiny diamonds within the metallic matrix, diamonds that had formed under the extreme pressures of the impact. This discovery attracted the attention of Karl Gilbert, one of the most prominent geologists of the era and the chief geologist of the United States Geological Survey. Gilbert visited the crater in 1891 and conducted a careful examination, seeking to determine whether it was of volcanic or meteoritic origin. Gilbert's investigation led him to a conclusion that would later prove to be incorrect. He reasoned that if the crater had been formed by a meteorite impact, there should be a significant mass of meteoric material buried beneath the crater floor, material that would create a detectable magnetic anomaly. When his magnetic surveys failed to reveal such an anomaly, Gilbert concluded that the crater was probably volcanic in origin, formed by a steam explosion or similar process. This conclusion, coming from such a respected authority, effectively closed the scientific debate for over a decade. The person who would reopen that debate was Daniel Moreau Barringer, a successful mining engineer and businessman who learned about the crater in 1902. Unlike Gilbert, Barringer was convinced from the start that the crater was of meteoritic origin, and he saw in it an opportunity for enormous profit. He reasoned that the impactor, which he estimated to weigh millions of tons, must still be buried beneath the crater floor, and that this mass of iron and nickel would be worth a fortune if it could be excavated and sold. In 1903, Barringer staked a mining claim on the crater and began a decades-long effort to locate and extract the buried meteorite. Barringer's conviction was based on sound reasoning, even if his economic assumptions proved to be flawed. He argued that the circular shape of the crater, the presence of meteoric material in the surrounding debris, and the disturbed nature of the underlying rock all pointed to an impact origin. He also noted that the rim of the crater was elevated above the surrounding plain, a feature difficult to explain by volcanic processes, but consistent with the ejection of material during an impact. Over the years, Barringer gathered evidence and published papers defending the impact hypothesis, gradually shifting scientific opinion in his favor. The mining operations, however, were a failure. Barringer and his investors spent over $600,000, an enormous sum at the time, drilling shafts and tunnels beneath the crater floor in search of the buried meteorite. They never found it. What they did not understand, and what would only become clear decades later, is that hypervelocity impacts do not leave intact impactors buried at the point of contact. The energy of the impact is sufficient to vaporize and disperse the projectile, leaving only fragments scattered across the surrounding debris field. There was no buried mass of iron to be found because the impactor had been destroyed in the instant of contact. Barringer died in 1929, still convinced that the meteorite was there somewhere, waiting to be discovered. He never lived to see his impact hypothesis vindicated, but that vindication would come in the decades following his death. In the 1950s and 1960s, advances in our understanding of impact physics, driven in part by nuclear weapons research and the emerging space program, provided the theoretical framework needed to explain how craters form at hypervelocity. Scientists realized that the energy of an impact is so great that both the impactor and a significant portion of the target rock are vaporized, making it impossible for a large intact mass to survive. The definitive proof came in 1960 when Eugene Shoemaker submitted his doctoral dissertation on Meteor Crater to Princeton University. Shoemaker, who would later become famous for his work on asteroid impacts and his role in discovering the Shoemaker-Levy comet that struck Jupiter in 1994, conducted a detailed study of the crater's geology and the shocked minerals found in its rocks. He demonstrated conclusively that the pressures required to form coesite and other shocked minerals could only be produced by a hypervelocity impact, not by any volcanic process. His work established Meteor Crater as a definitive impact structure and provided a framework for identifying impact sites elsewhere on Earth and on other planetary bodies. Shoemaker's contributions extended far beyond the crater itself. He recognized that impacts are a fundamental geological process, not just a curiosity, and that understanding impact dynamics is essential for understanding the history of Earth and the solar system. He helped establish the field of astrogeology and trained a generation of scientists to study impact structures, and he advocated for increased attention to the threat posed by near-Earth asteroids, a concern that has only grown more pressing in the decades since his work. When he died in a car accident in 1997, some of his ashes were carried to the Moon aboard the Lunar Prospector spacecraft, making him the only person to be buried on another world. Today, Meteor Crater stands as both a natural landmark and a scientific monument, a place where visitors can contemplate the forces that shaped it while standing on the same rim where Barringer once dreamed of riches and Shoemaker deciphered the physics of planetary collisions. The interpretive center at the crater's edge presents the scientific story in accessible terms, allowing anyone to understand the basics of impact geology without years of specialized training. And the research continues, with new studies refining our understanding of the event and its aftermath, adding detail to a picture that has been under construction for over a century. As you listen to these words, perhaps feeling the gentle tug of sleep at the edges of your awareness, consider how knowledge accumulates over time. Gilbert was wrong, but his careful observations contributed to the record. Barringer was right about the origin, but wrong about the economics, yet his persistence kept the question alive. Shoemaker synthesized the evidence and provided the theoretical framework that made sense of it all. Each contributed something, and together they built an understanding that none could have achieved alone. Science is like that, a collective endeavor unfolding across generations, each adding a piece to a picture that is never quite complete. Meteor Crater is not alone. It is simply one of the best preserved and most accessible impact structures on Earth, a representative example of a process that has shaped every solid body in the solar system. When we look at the Moon through binoculars or a small telescope, the surface we see is dominated by craters, thousands of them ranging from tiny pits to enormous basins, hundreds of kilometers across. Mars, Mercury, and the moons of the outer planets tell similar stories, their surfaces recording billions of years of cosmic bombardment. Earth has experienced the same history, but our planet's active geology, its moving plates and eroding atmosphere, has erased most of the evidence. Scientists have identified approximately 200 confirmed impact structures on Earth, ranging in size from a few tens of meters to over 300 kilometers in diameter. The largest confirmed structure is the Meteor Crater in South Africa, formed about 2 billion years ago by an impactor estimated at 10 to 15 kilometers across. The impact that created Meteor released energy equivalent to billions of nuclear weapons, enough to vaporize rock to a depth of several kilometers and send shockwaves around the entire planet. In comparison, Meteor Crater is a modest feature, but its youth and excellent preservation make it uniquely valuable for scientific study. The rate at which Earth is struck by objects large enough to create craters like Meteor Crater is estimated at roughly once every few thousand years. Most of these impacts occur in the oceans, which cover more than 70% of Earth's surface and leave no permanent trace. Others occur in remote regions where they may go unnoticed for centuries. The Tunguska event of 1908, in which an object estimated at 50 to 60 meters in diameter exploded over Siberia, flattened 2,000 square kilometers of forest, but left no crater because the impactor disintegrated in the atmosphere. Had the Tunguska object been metallic, like the Canyon Diablo impactor, rather than rocky or cometary, it would have reached the ground and created a structure comparable to Meteor Crater. The recognition that impacts continue to occur and that they pose a potential threat to human civilization has led to the development of systematic programs to detect and track near-Earth objects. Organizations like NASA's Planetary Defense Coordination Office maintain databases of known asteroids and comets, calculating their orbits and assessing the probability that any might strike Earth in the foreseeable future. As of today, no known object poses an imminent threat, but the catalogue is incomplete, and there remains a statistical possibility that an undiscovered asteroid could approach without warning. This is not meant to cause alarm. The probability that any individual will be affected by an asteroid impact during their lifetime is vanishingly small, far lower than the risk of countless everyday hazards. But the consequences of a large impact would be so severe that even a small probability warrants attention. An impact on the scale of the event that ended the Cretaceous period 66 million years ago, which was caused by an object roughly 10 kilometers in diameter, would be catastrophic for human civilization and potentially for the survival of our species. Smaller impacts on the scale of Meteor Crater would be locally devastating but not globally catastrophic. The study of Meteor Crater has contributed directly to our understanding of these risks. By examining the crater's structure and the distribution of its ejecta, scientists can calibrate models of impact physics that are then applied to predict the effects of future impacts. These models inform decisions about planetary defense, helping to determine how much warning time would be needed to deflect a threatening asteroid and what techniques might be most effective. The crater is thus not just a relic of the past, but a tool for protecting the future. There is something humbling about standing at the rim of Meteor Crater and contemplating its origin. The Arizona desert stretches away in all directions, seemingly endless and unchanging. Yet 50,000 years ago, a volume of rock larger than several football stadiums was excavated in seconds, hurled into the air, and scattered across the landscape. The forces involved dwarf anything humans have ever intentionally created, and the impactor responsible was, by cosmic standards, a small and unremarkable piece of debris, one of millions that orbit the Sun in our vicinity. This context helps us understand our place in the solar system. Earth is not a protected sanctuary, isolated from the violence of space. It is an active participant in the cosmic environment, subject to the same forces that have shaped every other body in the Sun's domain. The meteor that struck Arizona was not an anomaly, but a normal event in the life of a planet, one that has occurred countless times before and will occur again. Our advantage compared to the mammoths and giant sloths that witnessed the impact 50,000 years ago is that we understand what happened and can take steps to protect ourselves from future events. As the night deepens and your breathing slows, consider how thin the line is between normalcy and transformation. The Colorado Plateau existed for millions of years before the impact, and it has existed for 50,000 years since, with only a slight modification to mark the event. Life goes on. The desert adapts. The stars continue their slow procession across the sky. And yet, for a few seconds, everything changed in one small region, a reminder that the cosmos operates on scales and timelines far beyond our daily experience. Sleep comes, as it always does, and with it the quiet assurance that another day will follow. The crater will be there in the morning, as it has been for millennia, patient and still beneath the Arizona sun. One of the remarkable features of the Meteor Crater region is the quality of its night sky. The northern Arizona Plateau, with its high elevation, dry climate, and sparse population, offers some of the darkest skies in the continental United States. On a clear, moonless night, a visitor to the crater rim can see not just the bright stars and familiar constellations, but also the subtle glow of the zodiacal light, the faint band of the Milky Way stretching from horizon to horizon, and perhaps even the dim smudge of the Andromeda Galaxy, the most distant object visible to the unaided human eye. This darkness is not accidental. It is the result of geography, climate, and deliberate policy. Flagstaff, the nearest significant city, was one of the first communities in the world to adopt lighting ordinances designed to protect the night sky. These regulations, first enacted in 1958, limit the intensity and direction of outdoor lighting, ensuring that as little light as possible escapes upward to scatter in the atmosphere. The result is a region where professional astronomers can conduct sensitive observations and where ordinary people can experience the night sky much as their ancestors did before electric lighting transformed the human relationship with darkness. Lowell Observatory, located on Mars Hill just outside Flagstaff, has been in operation since 1894. It was here that Percival Lowell conducted his controversial observations of Mars, claiming to see canals that he interpreted as evidence of intelligent life. And it was here, in 1930, that Clyde Tombaugh discovered Pluto, using a blink comparator to detect the tiny dot of light that moved against the background stars. The observatory continues to operate today, conducting research on everything from the outer solar system to distant galaxies, benefiting from the dark skies that the region provides. For someone lying awake at Meteor Crater on a clear night, the view overhead is a direct connection to the same cosmos that produced the impactor 50,000 years ago. The stars you see are suns like our own, some larger and hotter, others smaller and cooler, each potentially hosting its own system of planets and asteroids. The Milky Way, that hazy band of light crossing the sky, is the combined glow of billions of stars, too faint to see individually, the disk of our home galaxy viewed from within. And somewhere out there, invisible to the eye but detectable by telescopes, are countless asteroids and comets, some on orbits that will one day bring them close to Earth. The connection between the crater below and the sky above is not merely poetic. Impact craters are formed by objects that originate in that sky, pieces of the same primordial material that condensed to form the sun and planets. When you look at the Milky Way, you are seeing the stellar nurseries where atoms of iron and nickel were forged in the hearts of massive stars, atoms that were later incorporated into asteroids and eventually fell to Earth as meteorites. The Canyon Diablo fragments scattered around the crater contain those same atoms, unchanged since they were assembled billions of years ago. There is a particular kind of peace that comes from contemplating these connections. The universe is vast and old, and individual human lives occupy an almost infinitesimal portion of its extent. Yet we are not separate from it. We are made of the same elements, subject to the same physical laws, participants in the same cosmic story. The iron in your blood was forged in a supernova explosion, just like the iron in the Canyon Diablo meteorites. The calcium in your bones, the oxygen you breathe, the carbon that forms the basis of every living molecule, all of it was created in the nuclear furnaces of ancient stars. In a very real sense, you are the cosmos contemplating itself, a pattern of matter that has temporarily become conscious enough to wonder at its own existence. As sleep approaches, let this thought settle over you like a blanket. You are lying on a planet that has been touched by the cosmos, in a region where that touch left a permanent mark. Above you, the same sky that sent the impactor 50,000 years ago continues its slow rotation, stars rising in the east and setting in the west, just as they have for billions of years. The crater will still be there tomorrow, and the next day, and for thousands of years to come. Nothing requires your vigilance tonight. The universe is proceeding as it always has, indifferent to human schedules and concerns, and that indifference is itself a kind of comfort. You do not need to hold anything together. You can simply rest, breathe, and let the night carry you into sleep. The people who studied Meteor Crater, from Barringer to Shoemaker, and the many researchers who followed, did so because they were curious about the universe and wanted to understand its workings. That same curiosity lives in you, or you would not be listening to these words. But curiosity does not require constant effort. Sometimes it is enough to simply be present, to let the information settle into memory without forcing it into immediate understanding. The crater will still be there when you wake, and so will the sky, and so will all the questions that make science such a fascinating endeavor. For now, there is only this moment, this breath, this gentle drift toward whatever dreams may come. The night over Meteor Crater is ending, at least in this telling. The stars are still there, of course, turning slowly overhead as they have done for billions of years. The crater itself rests in darkness, its walls catching the faint light of distant suns, its floor hidden in shadow. Somewhere in the desert, a coyote might be calling, or an owl might be hunting, or the wind might be the only sound, brushing across the sagebrush and juniper that have reclaimed the landscape since the impact 50,000 years ago. What remains after a story like this is not a list of facts to be memorized, though facts were certainly shared. It is something quieter, a feeling perhaps, or an image, or simply a sense of connection to something larger than the concerns of any single day. The impactor that created this crater traveled for billions of years through the void before its journey ended here. The rocks that were excavated and thrown across the desert contain minerals formed under pressures that exist nowhere else on Earth's surface. The scientists who studied this place dedicated their lives to understanding a few seconds of violence that occurred millennia before any human walked the planet. And you, listening to these words in whatever place you find yourself tonight, are part of this story too. Not because you did anything in particular, but simply because you are here, conscious and curious, taking in information about a world that existed long before you and will continue long after. The crater does not care whether anyone looks at it. The stars do not need observers to continue shining. But the fact that observers exist, that there are minds capable of wondering and understanding, adds something to the universe that would not otherwise be there. Sleep now. If sleep is what you seek, the crater will hold its shape through the night and through the years and through the centuries to come. The sky will turn, bringing new constellations into view and hiding others below the horizon. And somewhere, in the vast reaches of space between the planets, another piece of rock or metal may already be drifting toward an encounter with Earth, millions of years from now or perhaps sooner. It does not matter tonight. What matters tonight is rest and quiet, and the gentle knowledge that you have spent an hour contemplating something true about the universe. The desert wind blows, the stars shine, the crater waits, and you, wherever you are, can release the day and let the night take you wherever it will. There is nothing more required of you now, only this breath and then the next, and then the soft silence of sleep settling over everything like dust falling in a windless canyon. Good night, and may your dreams be as deep and peaceful as the Arizona night.